How's it going, ladies and gentlemen? Mr. Donnie here again, going over some SUPA Chem problems with you. We're looking at chapter 6.1 and 2, wave, nature of light, and quantized energy and photons. So let's take a look at number 1. It's kind of a definition question, like you either read it and you saw that or you didn't, and you probably don't know that. So which one of the following is correct? It'll be choice E. That is a formula we will be working with, so we want to be familiar with it. Remember that V looking thing is frequency. The upside down fancy Y looking thing, lambda, is the wavelength. And that C is the speed of light. Speed of light, which we usually use 3.00 times 10 to the 8th meters per second. Cool. So that is the first one. Looking at number 2. Of the following, blank radiation has the shortest wavelength. So shortest wavelength also means greatest energy. So if you didn't have a spectrum to look at, to consult, you could go, all right, well, which one of these things has the most energy? You might know more about that. So most energy, shortest wavelength would be the X-ray out of all those options. All right, number 3. Electromagnetic radiation travels through a vacuum at a speed of another definition. What's the speed of light through a vacuum? It's 3.00 times 10 to the 8 meters per second. We'll be using that quite a bit. All right, number 4. What is the wavelength of light in nanometers that has a frequency of 3.22 times 10 to the 14 per second? So we're going to have to call upon that formula we were just talking about. And it wants the wavelength. So that's the thing we're trying to solve for. So we rearrange it and we get wavelength equals C over V. So we got 3.00 times 10 to the 8th meters per second divided by 3.22 times 10 to the 14 per second. The seconds are going to cancel out. You're going to be left with meters, right? And you get an answer of 9.32 times 10 to the negative 7 meters. They want it in nanometers, so you just kind of convert that and you get 932 nanometers. Yeah, just a little algebra, you know, making sure you don't make a silly mistake and forget to convert meters to the nanometers. Even put that as an answer to throw you off, so that would have been a good wrong answer if there ever was one. 5. The wavelength of a photon that has an energy of 6.33 times 10 to the negative 18 joules is blank meters. So there's a new formula we're going to use now. Its energy equals lambda times frequency. All right? No. That's what I get eventually. Or you can also have energy equals Planck's constant times the speed of light over lambda, right? So we use that and we plug in Planck's constant, which is 6.626 times 10 to the negative 34 times by the energy, which is this, times by the speed of light over lambda. Solve for that thing. Just some basic algebra there. You should get answer B. All right? Cool. All right. I think I might have made a mistake on that, but you're tired to know. Cool. 6. Sorry, guys. Wavelength of a photon that has an energy of blank. So again, we're going to use the two formulas that we got, combine them. We're going to get energy equals Planck's constant times the speed of light over wavelength, right? Because if we look at the other one, we know that, oh, sorry, wrong one. Erase. How did I get that, Mr. Donnie? Well, I know that E equals h times the frequency. So I go, all right, well, what's the frequency? Well, I know that lambda times the frequency equals the speed of light. So let me rearrange to solve for frequency so I get wavelength. All right, so I get wavelength equals c over v, it's frequency, because I had to divide both sides by frequency. So now I can plug this in to, oh, I solved it for the wrong thing. Oh man, I'm dummy, right? Stop yelling at me. I solved it for the wrong thing. You rearrange it, you get V equals C on lambda. So then you plug that in to here, and you get this equation. So, all right, well, we got energy. We know that. Planck's constant is constant. C is a constant. The only thing unknown is lambda. So you just do some algebra, you solve for that, and you get final answer of A. All right, 7. Energy of a photon that has a wavelength of 9 meters is blank joules. So again, we're going to use that same formula. Energy equals Planck's constant times speed of light over lambda. They gave us the energy. All right, so check, we know that. Planck's constant is a constant, C is a constant. Now the only thing we don't know is wavelength. So that's just some algebra. I'm not gonna write it all out because you should be all right at algebra by this point. It's Ken. All right, cool. So the answer you would get is B. All right, 9, last one, a mole of red photons of wavelength 725 nanometers has blank kilojoules of energy. All right, so the first thing we're gonna have to do is figure out how many joules are in one photon, right? Second thing we're gonna have to do is we're gonna have to go from one photon to a mole of photons. And then we're gonna have to convert joules to kilojoules. All right, so first step. How do we figure out the energy of a single electron? We're going to use, or photon rather, E equals the hc on lambda. They gave us the wavelength. We'd have to convert that to meters. So we get 6.626 times 10 to the negative 34, running out of room, times by C over 725 times 10 to the negative 9 meters. Right? So we get 2.74 times 10 to the negative 19 joules per photon. That's for one photon. It's saying we have a mole. So how do we go from 1 to a mole? Well, what's a mole? Mole is 6.022 times 10 to the 23rd things in one mole. So if we had a mole of photons, we'd have to times one photon by that to give us 165,000 joules. Convert that to kilojoules, and you get the answer, choice D. Now I kind of rushed through some of the algebra, didn't maybe show all that. If you have troubles with that part, just, speak up in class, have me slow down, go over it. Hope you found that helpful. Hope you guys become experts. Hope you guys get it. Until next time.